This screencast is on kinetics, specifically on the rate law. So in the rate law, we are going to be focusing on as concentrations diminish as reactants diminish. So what we would do is look at A, if we're changing from substance A into substance B, as the amount of A decreases, the amount of B increases. And that makes sense because as we're reducing the amount of reactant we have, we're forming new product. So when we're doing the rate law, we're going to be looking at the reactants, and we're going to be using experimental data to decide how fast the amount of A disappears and B forms. The amount of a substance that is present would also cause the rate to slow down. So rates are not always a continuous straight line graph. They will have a curve in them. So if we have a lot of concentration of A initially, we may have a fast rate. And as we reduce the amount of A present, we would have a slower rate. So as we reduce the amount of A present, as we change it into B, you would see that down here the rate gets slower. So the ultimate goal is to write a rate law. And a rate law is an expression that allows you to see the factors of each reactant on how fast the reaction goes. And it is going to list the reactants, and it is going to have, we're going to be able to substitute in values and solve for pieces. So the rate law example I have here for you is that I have that we have NH4 ion plus NO2 ion makes N2 and water. And the rate law for this reaction is shown here. We have a rate, which is a speed, so that is going to typically be in molarity of some sort over seconds or minutes or hours, depending on how fast the reaction is going. And then we have a rate law constant. And the rate law constant will depend on the particular rate law. It is a calculated value, and it is a proportionality constant that allows this reaction to be correct. And then you're going to have listed your various reactants. You will not be able to look at the stoichiometry, so do not use coefficients to determine order, which doesn't make much sense right now. But I'm going to tell you that you may have a rate law that equals rate equals K, and let's say it might look like this. And it might be using the same equation, but you would not be able to look at the coefficients and determine this particular value here. It has to be determined using experimental values. What that's telling me is that my NH4 is a different factor than my NO2. So just like that example I showed you where I had the NH4 raised to the 2, and then I had NO2 with no power, and this was K equals rate. That is the order for the reaction, okay? The exponents that you're going to see after each concentration term are telling you how the order for the reaction. So with the number that's raised to a 1 power, it's considered to be first order. And if it's a second, it's second order. Third order. You usually only see zeros, ones, and 2. And you're probably thinking to yourself, well, why would I see 0? You're right. A 0, if you raise something to a 0 power, so let's say we take 2 to the 0 power, that would just equal 1. It's not a term that's going to be showing up in our rate law. So you're really only going to see understood 1s and 2s. If you get to a 3 or higher, there's something else going on, and we don't really deal with them here in class, but it could happen. So we can determine the order for each reactant, and then the overall order is the sum of the exponents. So the overall order in the case up here on the top, this is 1 plus 1, so this would be second order. And my version down here, I have a 2 plus 1, so this one would net me a third order. As I mentioned previously, rate orders do not correspond to the coefficients. The example I have shown right here is that it is 2 N2O5 yields 4 NO2 and O2. And the rate law, again, is built on the reactant. But you do not use the coefficient as your order. So this is a first order rate law, and it is determined experimentally. The units are dependent on the overall reaction order for the constant. So the constant units are the ones that we have to solve for, because you are always going to know that the concentration is molarity and the rate is molarity per second. So if you have a reaction that is like, let's say, rate equals K times one substance, we'll call it M. So we would have our rate, it would be molarities per second, and K, and then our single substance to a first order would just be molarity. If you solve for the K, you would have molarity over seconds times 1 over molarity. So if we simplified that, our units for K in a first order reaction would be 1 over seconds. You will also see 1 over seconds denoted with second to the negative 1. When they use a negative exponent, they're telling you that it goes on the bottom of the fraction. Here's a different case. If we have, let's say, we have a second order overall, so we have rate equals K, and we're going to go 2 substances. So when we plug it in our units, our rate is molarities per second. K is what we're looking for. We would have a concentration and a different concentration. So when we solve for K, we're going to have molarity over seconds times 1 over molarity squared, because molarity times molarity would get us molarity squared. So our K unit in this case would be 1 over seconds times molarity, which is also written s to the negative 1, m to the negative 1. So you can memorize the units for K dependent on the overall rate, or you can always solve them. And in fact, you will see test questions where they'll ask you to work through it and then calculate the unit for K.